What do the Egyptian pyramids, this viral math problem, and rational trigonometry have to do with each other? I don't know for sure, but I know the British flag is involved. Hello and welcome. Today I want to take a look at one of the cooler theorems I have ever come across, the British flag theorem. The British flag theorem has a number of different applications. There's a lot that we can do with it. We can prove that the opposite slant... Wait, I need something. All right, I got it. We can prove, ignore the bottom half here. We can prove that the opposite slant edges of a rectangular pyramid, when you square them, will sum to the same as the sum of the other pair of edges on the square pyramid. So the Great Pyramids in Egypt, which do have a rectangle, or roughly, I guess, a square as a base, if you squared the distances from the corners of the base to the top of the pyramid and added the ones opposite each other, the sum would be the same. Now, it's kind of awkward to keep saying the square of this or that, the square of the distance from the corner to the, oh my gosh, I'm even messing it up right now. And so there's another term for this. When we square a distance, we get something called a quadrant. This term comes to us from rational trigonometry, a discipline where we try to do trigonometry and geometry without irrational numbers. And the British flag theorem is instrumental in solving problems like this viral math problem, where we are going to find this distance x, which kind of seems to sit just sort of in the middle of a rectangle, and then we have these other three lengths and a circle that maybe are going to help us find that distance. Well, maybe. We're going to find out today. We're going to see. It all starts, though, with a rectangle. Let's establish the truth of the British flag theorem in the first place. The British flag theorem says that if we have some rectangle, later on we'll call the rectangle ABCD, but for now it's just some rectangle, and we place a point P on the interior of that rectangle. As we connect from corner to point P, and these are not quite diagonals, right? These are not diagonals, but they almost look like diagonals when you attach them across the figure. What must be true is that if you square this distance and then this opposite distance here, squaring those distances is called quadrants, and then we add them together, that sum will be the same as the quadrants here, the square of that particular diagonal looking object, plus the square of this particular diagonal looking object. Here's how we prove it. All right, let's keep this lo-fi as we figure this out. So we've got some rectangle. We will call it rectangle ABCD, and it has this point P on its interior. So eventually, I'll want you, the viewer, to prove that it does not matter whether P is in the interior of the rectangle or not. The lengths we're interested in, again, are from the corners to P. So we're going to draw in AP, BP, CP, and DP. And it gives us this thing that kind of looks like the start of the British flag, really to me looks more like an envelope. And then I'm going to draw in a couple other lengths. I'm going to go through the rectangle, up and down through point P, and then I'm going to do the same thing going side to side, again, making sure that this passes through point P. Hopefully you can tell that what we're creating are a bunch of different right triangles. I've got the one already drawn where AP is our hypotenuse. I've got another one here where DP is the hypotenuse, one over here where CP is the hypotenuse, and then finally I've got one over here where BP is the hypotenuse. To talk about these, let's come up with some labels. We'll call this L1 and this L2, and then up and down here we'll call this W1 and this W2. So you can tell, hopefully, W1 plus W2 makes the total width of this rectangle, and L1 plus L2 makes the total length of this rectangle. Let's go back to those right triangles and think about them in turn. So for example, right now, the right triangle with AP as a hypotenuse. This length here is also W2. Everything in here is right angles. Everything in here is rectangles. So we can say by Pythagorean theorem that AP squared is equal to W2 squared plus L1 squared. Now, importantly, we're going to leave everything in terms of the squares. This is where that rational trigonometry thing comes in. In rational trigonometry, we don't take the square root to get distance. We leave things squared to get quadrants. And so we're going to leave this AP squared. Now, I'm going to go in here diagonally so that I can capture these other two lengths in a right triangle. That is, I want to capture the square of W1 plus the square of L2, which added together by Pythagorean theorem is going to make the square of CP. This means we now have two of our different lengths. We only need to figure out two more. Let's do that same thing with BP, for example, which is going to come from this right triangle, which has its legs W2 and L2. And so we can say that BP squared is equal to W2 squared plus L2 L2 squared. And then finally, opposite that, we're going to figure out the square of dp, which is going to come from W1 squared plus L1 squared. That is the up and down length here is the W1, the left to right length here is the L1, and again, we're just applying Pythagorean theorem. So at this point, I have all four of those kind of diagonal-like objects, those lengths drawn from the corners of the rectangle to that point P in the middle. If we compare across these four different quantities, though, we'll notice something interesting. Each one of those partial lengths, W1, W2, L1, and L2, all have their squares represented exactly once on either side of this line. I've got W1 squared on the top as part of the sum for CP squared, whereas on bottom it's part of the sum for DP squared. And so on and so on. W2 squared represented up here as part of AP squared, and W2 squared represented down here as part of BP squared. And so the same thing for L1 squared, and so the same thing for L2 squared. Each one of these represented exactly one time. This is an equivalence. This is telling us that the sum of AP squared plus CP squared is the same as the sum for BP squared plus DP squared. This is the British flag theorem. But the truly crazy thing to my mind is it doesn't even matter if P is in the same plane as the rest of the rectangle ABCD. You can generate essentially exactly the same relationships when we take this into the third dimension and we look at what is basically a pyramid rather than simply a rectangle. We'll start with the same idea. If we draw these two lines and split the rectangle up into a width 1, width 2, length 1, and length 2, where in this case you could imagine some P prime that is the projection from the P above the plane of the rectangle down into the rectangle, we still have an AP squared, a CP squared, a DP squared, and a BP squared. I don't know why that's the order I chose. It's not the case anymore that AP squared is merely W2 squared plus L1 squared. Instead, that would be this length A to P prime. But if we connect P prime to P, oh my goodness, my graphing thing knew that I wanted to do this. What we see is another right triangle. This right triangle has hypotenuse AP, base length AP prime, and height of P prime to P, whatever that is. For no particular reason at all, we'll call that distance R, and what we get is a variation on the Pythagorean theorem that I like to call the super Pythagorean theorem. Again, A to P prime, that is the same thing as W2 squared plus L1 squared, and that comes from the original right triangle that we were drawing in 2 dimensions a moment ago. Remember, it's in perspective now, but that is a right angle in the plane of the rectangle. When you go into a third dimension, though, it's the case that this AP prime and R are the legs of the right triangle APP prime, where AP is the hypotenuse of that right triangle that exists now coming up from the plane of the rectangle. And so we could say AP prime squared plus R squared is equal to AP squared. But remember, AP prime squared was the same thing in that 2-dimensional rectangle as W2 squared plus L1 squared. So in fact, what we could say here is actually that W2 squared plus L1 squared plus R squared is equal to this AP squared in 3 dimensions. In fact, we can do that all the way down the line. That is true for every relationship in our, what is essentially a rectangular pyramid right now. For sure, that means that the same equality we were working with earlier still applies. The new AP squared plus the new CP squared is the same as the old AP squared plus the old CP squared plus an extra 2R squared. Just like the new BP squared and the new DP squared are the same as the old BP squared and DP squared plus an additional 2R squared. So the fundamental equality we're looking for our British flag theorem still applies here. It is still the case that the square of this particular length AP and the square of this particular length CP will be equal to the sum of this particular length BP and this particular length DP, the sum of the squares of those lengths. I think I said that. One thing this means that I personally never had realized until I started to work on this video is that for any rectangular pyramid, the sum of the squares of those kind of opposite slanted edge lengths will always be equal. When I was researching British flag theorem for this video, I came across this great wiki explainer, and wouldn't you know it, the wiki was brilliant brilliant.org's wiki. It walked me through exactly the derivation I needed. What I love about Brilliant is how it takes these geometric relationships that can feel a bit mysterious and turns them into something you can actively work through. Brilliant's courses help you build real understanding in math and coding with step-by-step interactive lessons. You're not just watching, you're solving, you're testing, you're seeing why things work. One course I used for the results and the animations in today's video was Brilliant's Coordinate Transformations course. It walks through how shapes move, reflect, and relate in the coordinate plane, which helps you build exactly the kinds of intuitions that underpin things like the British flag theorem. The courses are built by teams from places like MIT, Harvard, and Stanford, but they're designed to be approachable for anyone, from students just getting started to adults who want to go deeper. To learn for free on Brilliant for a full 30 days, go to brilliant.org/polymathematic, scan the QR code on screen, or click on the link in the description. Brilliant's also given my viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. I hope you'll check them out. Thanks again to Brilliant for sponsoring today's video. Now, in fairness, you might be wondering, what does this have to do with the viral problems on social media? No, not like those viral problems, the math problems that go viral, like this circle problem. You'd be forgiven for thinking, this kind of looks like British flag theorem, but there's a giant circle in the middle. Doesn't that make things different? And the answer is no, not really. This is, in fact, another application of British flag theorem. It looks a little different because of this circle, but in fact, we're going to see that it's exactly the same. One thing we'll do is we're going to bring up the center of this circle. And from the center of the circle, we're going to draw in 4 radii. You can see I'm connecting these radii to the segments that we were actually interested in. In the viral, though not to scale option, we can see those segments have lengths 34, 85, 10, and the unknown we're solving for, x. We want these 4 radii, and we want to recognize that these 4 radii are going to make right angles with the lengths we're interested in. And where there are right angles, there are going to be right triangles. As we connect each corner of the rectangle to the center of the circle, we can see 4 right triangles. And the hypotenuses of these 4 right triangles are the same lengths as the lengths of British flag theorem. And the hypotenuses of these right triangles are the same as the 4 lengths of the British flag theorem: AP, BP, CP, and DP. So what we have are 4 hypotenuses that match the lengths from our British flag theorem, and 4 radii, which of course are all the same. So whatever the equivalence we get from British flag theorem, we're also going to get that equivalence for these lengths we've drawn from the corners of the rectangle to the circle itself. Justifying that, of course, with something like Pythagorean theorem. For example, this length AP right here, that length is whatever it is, we have no idea. And for that matter, the radius is whatever it is, we have no idea. Let's call it r. What has to be true right now is that r squared plus 34 squared, 34 is the length of that other leg in the right triangle there, must be equal to AP squared. And we can do this over and over again for each one of the right triangles we created a moment ago. Up here, we've got a right triangle that has as its hypotenuse that length dp from earlier. And it must be the case that r squared plus 10 squared is equal to dp squared. Connecting that c to p earlier, we've got another r here and a right triangle, r squared plus 85 squared. Again, the 85 is this length here, not the hypotenuse, would be equal to cp squared. And finally, the actual one that we're interested in, x is the base of an r by x right triangle. So r squared plus x squared must be equal to bp squared. The key to remember is that ap squared plus cp squared had to be the same as dp squared plus bp squared. You could imagine subtracting away 2r squared on each side of this equation, and what you get is that 34 squared plus 85 squared must be the same thing as 10 squared plus x squared. 34 squared is 1,156, 85 squared is 7,225, just some nifty little math tricks that I'm using there. 10 squared is 100, and then x squared stays x squared. 1156 plus 7225 is 8,381 equals 100 plus x squared, and then we are just subtracting 100 on each side here to get that x squared must be the same thing as 8281. If we take the square root of that, we get our answer here for x, 91. There are some other cool ways to visualize the information that the British flag theorem is giving us. For example, by visualizing the actual literal squares of those distances AP, BP, CP, and DP. The British flag theorem tells us that the sums of the areas of those opposite squares will stay equal. That is, even as I move that point P around and even as the squares themselves change dimensions, what does not change is that the sum of their areas stays the same. 6.8 equals 6.8. I can get different values, I can get different areas, but 9.8 still equals 9.8. No matter where I place that point P, I'm always going to get the equivalence between those areas. Some interesting consequences for you, the viewer, to work through. The size of that circle in the center is variable. You can't solve for the radius of that circle just given these lengths. I have here the actual lengths. These are real, unlike the viral problem. And you can see that I can change the size of that circle in the center and it doesn't change the length. Now, of course, what will change the lengths is if I move the circle about, changing its location, but changing its size has no effect whatsoever on those actual lengths. I will leave that as an exercise for you, the viewer, to figure out. Thanks again to Brilliant.org for sponsoring today's video, brilliant.org/polymathematic. Please click the link in the description, scan the QR code on screen, type it into your browser like a T-Rex dinosaur. Give it to me in the comments. What is your favorite application of the British flag theorem? And I will see you all next time.